Okay, so that's my title. So I need to explain something to begin with. Now, I'm working out this proof as I'm presenting it, and that's obviously a very risky way to present anything. And one of the problems that comes along with that is sometimes you have a realization later on in the proof of something that you should have done a little bit earlier. So that's happened. And in the introductory talk, I gave an outline of the proof of this theorem, and I said primitive recursive a whole bunch of times. So I stated that we were going to define the primitive recursive functions and then prove that they are representable inside this system of arithmetic, which is the first order language of Robinson arithmetic, which I've labeled Q. The point is, there are also the general recursive functions, which is a broader class of functions. Now, in fact, I want to consider these instead because of a realization that I've had about a later point in the proof. Essentially, the primitive recursive functions, they're not what one would be familiar with when I say the computable functions. And so they're a little bit of an opaque class of functions in order to consider. The reason why you might consider them is because you might think that the Gödel's incompleteness theorem only holds if you consider such functions, but in fact you do have Gödel's result at a higher level of generality, which is for all general recursive functions. Now, the general recursive functions are in fact equivalent to all of the computable functions. Okay, so I really want to work within general recursive functions, and what that means is that you have to, go back into my previous talk, and everywhere where I said primitive recursive functions, you just need to say general recursive functions instead. Fortunately, I never actually gave the definition of what a primitive recursive function was. I only stated a property that these functions obey, and that property is still true on the nose if you just replace recursive functions with if you replace primitive recursive functions with general recursive functions anyway. So literally all you need to change is the word primitive to general, and then everything makes sense. So if that's clear enough, and I'm going to be defining this right now for the first time properly anyway, so I think it should be okay. All right. So general recursive functions are a class of functions from powers of the natural numbers to powers of the natural numbers. Well, what I mean by that is a Cartesian product of the natural numbers to a Cartesian product of the natural numbers, and they're defined inductively. Whoa.
Are you sure they have multiple outputs?
That's a good question. You don't have multiple outputs, I think. You only, yeah, so these are functions into the natural numbers, but they might come from.
Because they have to have one output to match the representability definition. Otherwise, you'd have to expand.
Yeah. Yeah. Sorry. No. These are only going to have outputs in the natural numbers, one copy of them. The general recursive functions are defined. So in the following set, psi. So we have the base case, and this is the constantly zero function, is general recursive. The successor function and then projections. use a different letter. Okay, so they're the non-inductively defined functions which are inside psi. And now let me define the inductive. Sorry, what did you say?
Could you read out what you just read at the bottom there? Just so it's
Oh, yeah, sure. Maybe that's not very clear. So that's just for any natural number n and another natural number m less than or equal to n. The function which represents pi superscript n subscript m from n copies of the natural numbers to the natural numbers, which maps a tuple k1 dot 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 up to kn, mapping to the elements km is in psi.
And
okay, so
is there any restriction on n? Because I don't think n would work if it was 0 or n.
Well, that wouldn't make any sense if n was 0, so yeah, for any natural number n.
Okay.
Greater than 0. Is that good?
Yeah.
Okay, I'll move to the next board. And now we have the inductive cases, and there's 3 of these. So the first one is composition. Cool. The next one is called primitive recursion. And it looks like this.
Wait, sorry, could you point out the could you actually define what the composite does to the input? Because I don't think it's necessarily clear.
Okay. Okay, so on an input k1 up to kt, we apply that input to each of the functions, h1 through to hm, and then we get m integers, which we can then feed into the function g. Okay, so back to... Is that okay?
Yeah.
Cool. So primitive recursion is... so the function f is going to end up being inside our set psi if there exists these other functions which are in psi, g and h, which satisfy the following. Yeah, I should probably use k here. Okay, so the way that you can think about this is when we give the function f 0 as the first input, it reduces down to this function h. So it's kind of like an inductive, or it's like a recursive definition. That's what the whole point is. So you've got this base case. And then if I give it an integer k plus 1, then that's equal to a function which is allowed to depend on the output of the function for, I just want to circle this, for the first input is j instead of j plus 1, and then we're still allowed to appeal to the rest of the input, which is k1 through the km, and we're allowed to depend on this integer j. So that's a definition which only makes sense once we've established this base case and the previous cases. So this is a recursive / inductive definition. Okay, let me see if I wrote the sentence here. So say f is a function, yeah, that doesn't make sense. So say it's a function, I'm just going to cross out in psi, for which there exists gh psi satisfying this, and then the sentence is then f is an element of psi. Okay, and what I have defined so far is the class of primitive recursive functions, but as I said, I want to go for the general recursive functions. So there's one more clause that I'll need to write, and it's the following. Such that for all, I keep using n. Let me make that k. No, I wrote this badly. Sorry, let me go back here. Okay, crushed that into the corner there. So let me explain what this is saying. So if f from n to the m to n is a function which satisfies the following property, it's that for all k1 up to km minus 1, there exists a k such that f of k, comma, k1, comma, dot, 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 comma, km minus 1 is equal to 0. Then the function which on k1 up to km minus 1 maps to the least k such that f of k, comma, k1, comma, dot, 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 comma, km minus 1 is equal to 0, that function is inside psi. Great. And then psi is the set of general recursive functions. Any questions about that definition? All right. So I also want to define general recursive relations. which just
Sorry,
piggyback.
I was wondering if you had a quick example of a simple example of a use of minimization.
A simple example would be, well, do you want an example for which I can't use the previous axioms? Because I think that is not necessarily that simple.
No, just like minimize any function. Like,
well, I can, if f k1 to k2 is k2 minus 2, then mu f on k2 is equal to k2. Does that make sense? Because what this does is it returns the smallest input for which this wait, no, not minus 2. If I make that minus k1.
okay.
Yeah, so that's the minimal value for k1 for which k2 minus k1 is equal to 0. That minimal value is going to be k2. Does that make sense?
Yep.
Okay, so it's the minimal argument as well, by the way. It's not f of that minimal value. It's actually the minimal argument which we want to be able to return.
Right. Because otherwise you just get 0, and that wouldn't be very productive.
Yes, exactly. And the classic example of a function which is general recursive but not primitive recursive is the Ackermann function, but I kind of just want to leave that stated out loud because I haven't personally checked whether that is general recursive and not primitive recursive. But depending on how heavily I'm going to be using this final clause, the minimization later in the argument, I might present that function in order to help with intuition of the gap between primitive recursive and general recursive. But I'm not so sure it will be that important. The difficult parts of the proof later on, in fact, are going to be dealing with the primitive recursive clause, not the minimization clause.
I might add like a quick characterization. You can also capture the general recursive functions by starting with the primitive recursive functions, so just everything up to this last clause. And you can get all the general recursive functions by just one use of minimization. That's a theorem you can prove about the general recursive functions that, that you can essentially just minimize a single primitive recursive function, and that allows you to access every general recursive function. Yeah.
Okay, cool. All right, sounds good. I think Russell's playing with a third board. Shall I move to the first board again, or do I kick him off?
I think just clear it.
All right. Okay, so let me just quickly write down what I mean by general recursive relation, as this is going to be very important. Cool. So that's it. You have a relation in your hands, and you're wondering if it's general or recursive or not. And all you do is you construct the characteristic function, and then you ask yourself whether that is general or recursive or not. And we'll just point out the small slight oddity that I'm using 0 in case k1 up to km is an element of R, and then 1 if k1 up to km is not an element of R. Truth be told, I don't actually completely know why I'm using that convention, but every resource that I've found for Gödel's incompleteness theorem so far uses this convention, so I'm slightly terrified of it. I'm worried that later on that's going to become very important. So we'll stick with it, and I'll be sure to mention it if it does come up a little bit later. For the history nerds out there, Gödel himself used this in his paper as his definition of characteristic. It's a little bit interesting.
I have a feeling it's just down to like, if you want to have like, if you want the characteristic function to involve like equality between two numbers, then you get their equality by checking the distance between them, and then to then convert that into one, like just for the sake of it, it's just like an extra step, I guess.
Yeah.
That's my best guess.
That's a good point. I imagine it's something like that as well. Okay, so one small remark that I'll make on the definition of general recursive function that I gave is in the clause on primitive recursion. So which, recall, is the second inductive axiom that I gave. We do allow for the case when m is equal to 0. And so spelt out, what that means is if f from n to n sorry. The way this works is if g is a function which is inside psi, and h is simply a natural number, satisfying the following. So f of 0 is equal to that natural number h, and then f of, that's different to how I wrote it earlier. So f of the successor of j, so I'll just keep consistent with my notation and write f of j plus 1 is equal to g of j comma f of j. Then f is an element of psi. So just flag that that is also allowed. And in fact, that's a case that we're going to use a lot. Okay, so I'm about to give some examples. So let's go ahead and do that. I'll jump over to the first board again. Okay, and for the most part, these examples will not merely be general recursive functions, but they'll be primitive recursive functions as well. But I'm very unlikely to actually use that fact. What we care about is the fact that they're general recursive. Okay, so if I define this function sg, essentially sg is equal to 0, sg of 0 is equal to 0, and then sg of j plus 1 is equal to 1, which is equal to the successor composed with the 0 function applied to j plus 1. Then this is general recursive. Cool. So I've used primitive recursive in the m equals 0 case, along with composition of the basic functions which are the successor and the zero there. Another important one is the same thing, but with the values swapped. So SG bar of 0 is equal to 1, and SG bar of j plus 1 is equal to 0 is also general recursive. And that one's helpful for proving that if you have a proposition that is represented by a relation which is primitive recursive, then the negation of that relation is also primitive recursive. Okay, we can define the predecessor easily. So this is just P of 0 is equal to 0. And then P of j is equal to j.
Much easier than predecessor function with church numerals.
Yes, much easier. Is general recursive. Okay, and we'll also look at cutoff subtraction. So I'll just denote this as 0, negative brackets 0, comma x. So how is that read? That's read as x minus 0. Okay. And negative of j plus 1, comma x is equal to the predecessor of negative j, comma, well, sorry, I'm in trouble with the whiteboard. J, comma x. And that gives you cutoff subtraction. And what I mean by that is if the result is a natural number, then you return that natural number. But if it becomes, quote unquote, becomes a negative number, that's an ill-defined statement, but whatever. Okay, so y minus x is equal to, so what is it? It's equal to the z such that x plus z is equal to y if such a z exists, and it's equal to 0 otherwise. That's what this function is. Okay, and another helpful one is the distance function. And so this is the distance between 0 and x is simply equal to x, and the distance between y and x is equal to negative y, comma x plus negative x, comma y. Cool. So that's not equal to 0 because that's the cutoff subtraction, don't forget. So if y is not equal to x, strictly one of those is non-zero. And so it just gives us the distance. Okay, so hopefully that's a good list of examples. Hopefully that starts to build up your intuition of the way that we define general recursive functions. But that's not the only reason why I described this. It's also that the general way of describing complicated general recursive functions is to build up a repertoire of more simple ones and then use them in order to describe more complex ones. And the same is true if you look at general recursive relations. So we're going to be doing that very heavily later in the proof. But for now, I just wanted to prove a couple of simple lemmas that describe...
Just quickly,
yeah.
You made use of addition, so it should be pointed out that, like, for the distance function, you're relying on the fact that addition is a primitive recursive function.
Yeah. I think I'll be using I'll be using multiplication later as well, so I'll leave that as an exercise too. Okay, but I want to build up propositions. I want to say if we have a relation that's described via a property. What about the relation described by the negation of that property or the disjunction of that property? So that's the next thing that I'm going to describe. Cool, I'll jump to the next board. So two further examples are, so these are general recursive formulas this time. So n equals m and n less than m are general recursive. Okay, I guess I should be a bit more precise than this because this actually confused me a little bit when I was reading this to begin with. So these might look like formulas that have been constructed in, oh, why did I say formula? Okay, that's very confusing. I actually mean the relations here. So I mean the relations that are described via these formulas, right? So you might identify that these are formulas that are able to be constructed using the first order language that we've been describing. Or in fact, the second one isn't, n less than m. We haven't spoken about, we didn't have any relation symbols inside Q, so n less than m is not a formula that's describable. So I'm kind of using these as meta descriptions of the relations. So for instance, n equals m, what that really means is the relation delta, a subset of n squared, where n m is an element of delta if and only if n is equal to m. Okay, so that's a bit of lazy shorthand notation, but that's what I mean by it. These in general recursive, they have characteristic functions respectively given by SG distance between n and m and SG m minus n. Cool. So that's very, very basic. The equality predicate and the less than predicate give rise to relations which in general are recursive. That's something that we can prove with the examples that we've seen so far. Okay, let's have a look at something more complicated. Then so are the complement of R and the union of R and S. So I'll write down the characteristic functions for these. So the negation is just SG bar composed with the characteristic function of R. And for R union S, what you do is you take the characteristic function of R and you multiply that by the characteristic function of S. So keep in mind that 0 means that it is in the set, right? So it's going to, so in integer n is an element, is going to get mapped to 0 under this map if either one of the characteristic function for R or S map it to 0.
So by this multiplication, you mean the function that takes the input, feeds it to both functions, and then multiplies the outputs of those functions.
Good. Okay, and so that's the end of the proof. So the intuition behind this lemma is if we have a formula that describes a relation, then the relation that's described by the negation of that formula is also primitive recursive, and then disjunction as well, P or Q. right? Okay, and then conjunction and implication can also be described in terms of those two things that we've given, disjunction and negation. And so therefore you also have P and Q, and you also have P implies Q. If P and Q are your formulas that are describing your relations R and S, that can also be proved directly, though. It's not necessarily something that you have to build up from disjunction and negation. Okay, I'll leave that, simply spoken out loud. So let's look at one last lemma. And this is going to be looking at bounded quantification. So the intuition going into this lemma is that if a relation is general recursive, then bounded quantification upon that relation remains general recursive. So let me make that precise.
Does quantification like reduce the number of like the arity of the relation?
Yes.
Right. Yeah.
Wait, does it? Maybe it doesn't.
Right. Wait, because it's just starts as a set of natural numbers, not like a.
Yeah, exactly. So it actually won't reduce the arity of anything. No, sorry, I take that back.
So wait, what does it mean then? Like, what is?
Well, I'm about to write it. Let me get the formals down. Okay, so this is E. This is for existential quantification. So this relation is n's an element of E if and only if for all x in natural numbers, x is less than or equal to f of n, and n is an element of R. Wait, that doesn't make any sense. I haven't written x there. Oh, that doesn't even make any sense.
F of n is larger than every natural number.
Oh, that doesn't even make sense. What am I meant to write there? Yeah.
Is it supposed to be like? Is n supposed to be in?
It's just x here.
It's just x.
Yeah. So x is less than or equal to f of n. And then this is not meant to be for all. This is meant to be there exists. Okay, that statement makes sense. Where n's in E, if and only if there exists an x less than or equal to f of n, such that x is an element of R. That makes sense.
Okay, so it means something before f of n is in E.
Mm-hmm. Yeah.
Okay, yeah.
And then for all is if all of them are in. Oh yeah, I've written. Yeah. So you just said in E, but you meant to say in R.
Right. Yeah.
Cool.
I'm thinking about if there was no f at all and it was just like x is less than or equal to n, because that would seem like the most straightforward kind of existential quantification or universal quantification. But this is also just allowing for if you want some.
Yeah, that's exactly the point. Yeah. Yeah. So, and keep in mind that f has been asked to be general recursive. So the point is thinking about general recursive functions as computable. It's like if you have some computable bound is essentially what this says. But obviously the canonical example is f of n is just equal to n. So it's bounded quantification. Okay, and I'll prove this over on the other board. Proof. Okay, so looking at A to begin with, I just need to construct a general recursive function, which is the characteristic function for it. And I'll do that like this. So I take the characteristic function of A applied to 0. All I need to do there is check 0, right? Because I can only be less than or equal to, sorry, it's actually f of 0. That makes sense. Wait, does that make sense?
Doesn't it have to go all the way up to f of 0?
No. So I think I just want to write this because
Because 0 is in the relation if and only if every number up to f of 0. Oh, sorry, there exists a number up to f of 0, which is in the relation, right? Which is in R, right? Yeah.
Okay, I think that fixes it. Now that works because f of 0 is a fixed constant. So that's nice and easy. I can just construct that. No problem.
Wait. But is this supposed to be by primitive recursion?
Yeah, so this is an integer.
I don't think you can just define it to be take the product of all of these things.
Why not? That's an integer, right? So I've got chi r, and I can just work out chi r of f of 0 and all the others, and I can multiply all of those, and that's an integer. That's either 1 or 0, and I'm just setting chi e of 0 to be equal to either 1 or 0.
When you use primitive recursion, so this itself, this is like the function h, right? In the definition.
Yeah, but keep in mind in the case that I'm using, h is just a natural number, right?
Right, but this. Oh, okay.
And that is an actual number when I've written down.
Yeah, okay, I understand.
Okay, cool. And then this is similar. So
yeah, I don't know how you can do this step though, because what if this one is like, doesn't this depend on fj plus 1? Like it could be way bigger. Like there could be not just one more number to check, but like a whole bunch.
yeah, but that's fine because we're looking at
Right, but what if there's a large gap between f1 and f2? Like F2 is much greater than F1. And there's a bunch of options between them.
Yeah, I see. So this is checking if I see. This doesn't check all of the x's less than or equal to f of n. That's what you're saying. This only
it just checks.
to equal 1. Yeah, that's
Do you need to apply f to x as well? Because then it would be only the. I mean, I don't know. I don't know if that would fix it.
Look, what I want is chi r of f. Yeah, so if I was looking at chi a of n, that's meant to be chi r of f of n times chi r of f of n minus 1 times dot 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 times chi r of 0, which means all I need to do is write that as chi r f of n times chi r f of n minus 1 times dot dot dot. And that has to go down to, pardon?
That's what you just wrote.
That's not what I just wrote, is it?
Oh, well, okay, the last bit's different.
Yep, and then I want to do chi e of f of n minus 1. Yeah, that makes sense. So I need to write this, and then I need to check that this is a valid general recursive definition. So that's how do I write? I need to work out how to say this. Stop at f of n minus 1 plus 1.
I think you could just make it stop at 0. What you wrote after want, I think that itself can be a a primitive recursive function, or it's a general recursive function. But it would sort of it would be clean to define it separately and then use that as a part of the definition of chi e and chi f.
Yeah, I see, that makes sense. So if I just say, let me switch to black.
Yeah, just use a different function altogether. I suppose it still does depend on chi.
Well, I think chi e of n is chi r of f of n times chi e of f of n minus 1. That makes sense. Oh no, that doesn't work still.
Right, because we want the output of chi r of n, and also chi r of n minus 1, and also we're making use of.
Wait.
I don't know. I think what.
No.
Wait, we might be doing different things here, but I think you can separately define the function which checks if all numbers up to n are in the relation R, and then later like apply f to that before you throw it in. So I don't know, like theta of n, theta of 0 equals chi r of 0, and then theta of n plus 1 equals chi r of n plus 1 times, well, is it plus? Because 0 means in the relation.
Yeah, we just want any one of these to be. So we want to look at multiplication.
Oh, okay, multiplicated. Yeah. Okay, so you have that function. Now make use of that for chi-e. So it would be theta of f of n.
Why did that not just work earlier?
Wait, so I think you I suppose that is a definition of chi-e.
Yeah, that's like exactly what I had here, but
yeah, it just matters. It matters what you like perform the primitive recursion on, and in like because we're not like involving this wild function f in the with the primitive recursion, that like we're able to multiply all the correct numbers together.
Yep. Yep, I agree. Okay, what if I just clear this board and rewrite that small proof?
Okay.
Okay, thanks for the help. Okay, cool. So what the function theta does is it just checks whether n is in R for all n. I shouldn't have said n. So what theta does is it checks whether m is in R for all m less than or equal to n, but then we want to apply that to f of n because we have this computed bound. So we just apply f to n and then feed that to theta. That's how we get this function. And then for f, it's similar. So first I'll define nu of 0 is chi r of 0, nu of j plus 1 is nu r of j, and then I'm going to, Sorry. And I'm going to write plus here because the point is I want this to be 0 only if all of them are equal to 0. Okay, and then, so not actually, oh no, yeah, that makes sense. So then the characteristic function of f applied to n is Sg of nu of f of n. And the role of the Sg here is if we don't get 0, so we get something is not in something less than or equal to f of n is not inside R, then nu of f of n will return at least 1, but there might be more things that aren't inside R that are within that bound. And if there's more than one thing, then nu will return an integer greater than 1, and we need it to just return 1. So what you do is you just feed this function through Sg, and then you're done. Okay, that's a proof. So the way that you want to think of the previous lemma is that it's giving you that bounded quantification still lands you within general recursive relations. Cool, and then we'll build up things beyond there as well. Okay, next lecture I'm going to talk about representability, which is the very important property that general recursive functions obey, which I presented inside the lecture 1. But in that lecture, I said that it was true of the primitive recursive functions. It is indeed true of the primitive recursive functions, but it turns out to be true more generally of the general recursive functions as well. And that's the result that I'll be using, and that's the result that I'll be proving. Okay, I think that's it for today. Does anybody have any questions?
I think that's just going to add we're also altering the definition of representability, right?
Oh yeah, that's true. Yeah, so that will be slightly different to what we wrote in the first lecture as well.
Great, thanks, Will.
But again, not significantly so. Yeah, no worries. Thanks a lot, Billy, for your help doing that. That was really helpful.
No worries.
Okay, I guess that's it.